Good afternoon, everyone. My name is Li Ren. Today I'm going to introduce our research work on image description task. First of all, I want to apologize for not able to come to the conference, and I also appreciate that the conference allowed me to have this chance to present this work through this video. Our work is improved image description that embeds object structure graph and semantic feature matching. And this work is collaborated with Dr. Kim Hua from UCF. Let me first introduce the image description task. The image description task or image captioning task is to teach the machine how to understand the content of the image and then translate into natural language. The input of our system is a raw image and the output is a human-readable sentence. The sentence describes the semantic content of the image. For example, look at this image. It shows two players playing baseball game. The system reads the image and expects to explain it with a sentence such as the sentence on the right-hand side. And first, let me introduce some basic framework, our basic concept of image description. With the help of modern deep learning technique, the XT method is based on the sequence-to-sequence framework. The framework is combined with an encoding model and a decoding model. So let's see this graph. The encoding model on the left, there is a raw image sent into a convolutional neural network, and then it will be encoded into a feature vector. On the right-hand side, the feature vector is further decoded by a sequential model. The sequential model is always constructed with recurrent neural network, such as the recurrent unit or the long short-term memory. The sequential model generates the sequence of words that it samples from its distribution. As we can see that it generates words one by one, and at each time the model generates a new sample words based on the previous word. For example, here the word baseball is generated based on the word A, and the word player is generated based on the word baseball. So let's briefly review some previous works. Previous works provide various decoder models to improve the understanding and explain the image. In 2015, the researchers applied attention mechanics on the spatial domain of the image, and it helped the model to learn how to focus on some local regions during the sentence generation. The work in 2016 further applied the attention on the detect concept work instead of the image itself. That makes the description more accurate, and in 17, a better result is achieved with more complex decoder, where the model is based on the multilayer fusion of the detect objects. And now in 18, the current model focuses on some very dense local region features, which is from some very large data set that has very dense label on it. And the very dense feature also pushes the accuracy of the understanding. So we can see that convolutional neural network, or CNN, plays an important role in the sequence-to-sequence framework because it detects and understands object inside the image and then constructs a sentence with it. However, the CNN framework that reads the global content is most likely to pre-train on some image classification task, and the model technique proposed to apply the regional CNN or the RCNN to accurately detect the local objects. Here's an example shows our baseline model detects objects and generates a description. We can see that the result sentence here mentions all the objects and connect them with a simple sentence structure. So the limitation of our current method is the capability of detect objects is too strong. It's very strong, but the intrinsic connection between objects inside are always ignored. So in this work, our motivation is trying to learn the organized object structure where they connect with each other. In other words, we want to modeling the geometric structure based on the detect object and learn from this RCNN, and hopefully it can help us to learn to explain of their relationships inside. For example, here our model learns the connection between the woman and the bike, and the man and the horse, and or the woman and the horse. So we can see that the second sentence is generated by our model, and where we know it contains some more information about the positioning and the relationships between the objects. So also we apply the attention mechanism on the pairwise relationship learned by our model, and instead of the isolated objects like other works. And here we show some example. Our model learns to weight the pairwise objects, and we see that the informatic object pairs, the meaningful object pairs, the man and the horse and the woman and the bike, were learned with a higher weight by the attention mechanism. We first detect objects from the raw image, and then retrieve their dense feature from the RCN network. We also extract global content with the original scene as the reference vector. And this step is same to the self-art techniques. With detect object, in addition, we record their relative distance and directions in order to integrate the structure between the objects. And to integrate the relative direction and the distance from one object to another, in this example, we encode the distance into one of the 7 classes according to their normalized distance, and also encode the direction into one of 8 regions, according to their angle relative to the horizontal line. So the original feature vector is embedded and concatenated with the encoded feature. We see that the distance are encoded into 7 bits and directions into 8 bits, and we also encode the spatial pattern that tell us how the 2 objects are overlapping with each other. The model of the subregions contains 2 bounding box. We encode them with 2 bits label, includes first object, second object, and background and the overlapping area, and then we pass it to another CNN to encode. And we want to integrate the graph structure, include all the objects and relationships, not simply accumulate with the object pairs. In order to do this, we propose an embedding framework with the help of GNN. Since we know the category of the detect objects represent objects with their classes, and integrate those classes into a sparse matrix. This matrix integrates a pattern that contains relationships between the categories inside the image. And then we embed the matrix with the 3 convolutional layers and to learn the hidden representation. We see that with the help of CNN, the geometric relationships between the class construct a unique pattern that are easily to integrate into a vector. In order to search a more representative embedding, we further match our hidden vector with the corresponding sentence labels. And the motivation is that we want to search the encoding objects that has high correlation with the sample in text domain. We embed sentence with another CNN in text domain, where each words are added into a word vector, and then we concatenate them together and apply the CNN on this feature. So the embedded feature has the semantic contents of the sentence. For the matching process, we apply the marginal-based ranking loss, and which is widely used to match samples from different domains. And the motivation is the matching is trying to reduce the distance between the correct pairs, and meanwhile to enlarge the distance of the incorrect pairs. So we implement ranking loss within the batch that contains only one correct pairs, and all other pairs are incorrect. Here, in our formula, we can see that the model is trying to maximize the similarity between the correct pair, such as the GA and the SA, while minimize the incorrect pair, the GA to SB and the GB to SA. And we evaluate the model on two popular dataset. The MS COCO that contains about 112,000 images, and for each image they labeled 5 sentences, and we follow the splitting in other works where they sampled 5,000 samples for validation and 5,000 for test. Another data set we try is Flickr 30K. It's a classic data set that contains 30,000 images and with 1,000 samples for validation and 1,000 for test. So our splitting is consistent with other recent captioning works in order to compare with them fairly. And we test the result with the popular matrix such as Metro, Blur, and ROS, and the CIDER that is widely used to evaluate the translation model in NLP and other visual computing area. Here we see the experiment result. We made a application study with combination of object graph, matching, and original global vector. We see that the object graph and the matching provide some significant improvement compared with our baseline and other settings. And finally, our settings that integrate all of the features outperform our other settings. And we also compare our results with some other works, some state of art in the 17 and early 18, and all results on both data set we can see has competitive performance in the single model, especially in BOU. And know that all of the results we list here is a single model in single task result. And here's some select results we show in our paper. We see the sentence generated by our model contains more positioning information and details, and comparing with the baseline results, we have more accurate description to interactive between the objects. Here we introduce our conclusion. We build a framework to generate image description with our embed object structure graph. And we introduce a novel way to encode a graph based on the geometric information and detect object. And we also designed an efficient way to encode our graph. Our encoding is normally based on the structure of the categories instead of isolated objects. And we also propose a marginal-based semantic matching schema to learn the representation that is highly correlated with the reference sentence. And finally, our experimental results show the effectiveness of our caption generation with the help of our object structure graph. So this is the end of our introduction. If you are interested in more detail, please refer our paper and poster. Our paper ID is 12, and you can also ask me questions via email. Thank you.